All right, let's jump right in. Today, we are going to break down one of the absolute cornerstones of reinforcement learning, dynamic programming. Now, I know the name sounds a little intense, maybe even a bit scary, but I promise by the end of this, you're going to have a really solid, intuitive feel for what it's all about. So let's get to it. So, let's start with a big question to frame this whole thing. Imagine you're playing a game, but it's a game where you know everything. You know every possible move you can make. You know what happens after every move. You know all the points, all the rules. The real question is, with all that perfect information, how do you find the absolute best, most unbeatable strategy? In the world of reinforcement learning, that's what we call a planning problem. And dynamic programming, or DP for short, is the classic go-to solution for it. Think of it as the ultimate tool you pull out when you already have a complete map of your world and all you need to do is find the best possible path through it. Okay, to make this whole concept really click, we're going to use a simple analogy for the rest of this explainer. So, forget about all the jargon for a second. Agents, states, rewards, just picture this. Our mission is to create the perfect GPS driving guide for a small town, a guide that will tell us the absolute fastest way to get home from any intersection in the entire town. First step, let's define a key term, policy. What is it? Well, in our analogy, the policy is just your current driving guide. That's it. It's a big book of instructions, and for every single intersection, it tells you exactly what to do. Turn left, turn right, or go straight. It's your current plan. And next, we have the value function. Sounds complicated, right? It's not. Just think of it as your time-to-destination map. It works hand in hand with your policy. For every intersection, it tells you, hey, if you're standing right here and you follow your current guide perfectly, it's going to take you this many minutes to get home. It's basically how we grade our guide and see how good it actually is. So, how does dynamic programming actually create that perfect guide? Well, it uses this really elegant and powerful two-step rhythm. It's a loop. First, you grade the plan you currently have. Then, you use those grades to make the plan better. That's the whole dance. Grade, improve. Grade, improve. So let's look at the first part of that dance. You have a driving guide. Maybe it's a random one you just made up. The very first thing we have to do is figure out, for real, how long does it actually take to get home from every single spot if we follow these instructions? This process has a name, policy evaluation. We take our time to destination map and we make sure our time estimates are totally accurate for the guide we're using right now. We keep tweaking and updating the times for every intersection until they all make sense together and are perfectly correct. And you know, the logic behind this is incredibly simple. It's really the core idea of the famous Bellman equation. It just says this: the time it takes to get home from this intersection is just the time it takes to drive to the next intersection, plus the time it takes to get home from that one. That's it. We just apply that simple piece of logic over and over and over until all our time estimates are rock solid. Okay, so we've done part one. We've accurately graded our guide. We have a perfect time to destination map that tells us the truth about our current strategy. Now we get to ask the really fun question. Based on these accurate times, is there anywhere, any intersection, where we could make a better turn? And this step is called policy improvement. And honestly, it's as straightforward as it sounds. You go to every single intersection one by one. You look at all the possible ways you could turn, and you ask a simple question. If I turn left here, is my total trip home going to be shorter than what my current guide tells me to do? If the answer is yes, you just get out your eraser, you change the instruction in the guide, and you write in the new, better one. You just make the obvious, common sense choice everywhere. So let's just make this crystal clear. The two steps are very different. Policy evaluation is a passive step. You're just doing the math, you're grading your plan. You don't actually change the driving guide at all. But policy improvement, that's an active step. That's when you're actually taking action and changing the instructions in the guide to make it better. All right, now for the magic. Let's put these two ideas together and watch how this simple loop builds the perfect plan from scratch. This is the whole thing right here, the policy iteration loop. First, you start with a completely random, probably terrible driving guide. Then, step 2, you evaluate it perfectly. You calculate all the real travel times. Step 3, you improve it by finding all the smarter turns. Now you have a new, slightly better guide. So what do? You just repeat. You evaluate that new guide, then you improve it. And you just keep going around in that loop, evaluate, improve, until you go through a whole cycle and realize there are no more improvements to make. And here is the core magic of dynamic programming. This simple back and forth process is mathematically guaranteed to find the best answer. When that loop finally stops, when your guide doesn't change anymore, you are holding the single best, fastest, most optimal driving guide that could ever possibly exist for that town. It's perfect. So, we've gone through a lot. If you're going to remember just one thing from all of this, let it be this next idea. This is the whole concept boiled down into one sentence. Dynamic programming finds the best plan by repeatedly improving its guess about how good the current plan is. See? It's that two-step dance. You figure out how good your strategy is, and then you use that new knowledge to make your strategy just a little bit better. You do that over and over and over again until it can't get any better. But that brings us to one final, really important question. The entire power of dynamic programming relies on having that perfect map of the town to begin with. So, what happens in the real world when we don't have all the rules? What do you do when you have to learn the map as you go? Well, that's where the rest of reinforcement learning comes in. Thanks for tuning in.